object store, there's no single point of failure. The idea is you can scale up to large amounts of storage, and it should be able to run on commodity hardware. Now, the Ceph data, you can access it in a number of different ways. One way is through the Ceph object store. This is a RESTful interface that's compatible with S3 and Swift APIs. So a lot of cloud technologies use these. You can access the data through a Ceph block device, also called a Rados block device. So this is like a virtual block device that's distributed over the cluster. You can access the data through the Ceph file system, which is a POSIX compliant file system that's also distributed over the cluster. So these are the three main ways you can access data with Ceph, and we'll go over those in a bit. So we're going to take it like one layer at a time. So at the host level, so at the machine level, the machine can have a number of object storage devices, and it can have a monitor or monitors. So the monitors, their whole job is to monitor the cluster, keep track of where the object storage devices are, etc. You can also use them to kind of be aware of the physical layout of the machines, and you can do like a failure domain kind of thing to make sure you don't go all down if something bad happens. Now the object storage devices, they're what actually store the Ceph data objects. A host can run multiple OSDs. You need to be equivalent specs. So for example, each machine, you can have as many OSDs as you have hard drives. But of course, you want to make sure that the other I/O is capable of handling that, and you have a good balanced system. So that's kind of something that maybe a data center architect would define how they want to deploy their cluster. So there's not really a one size fits all. It depends on what you're looking for. At the block device level, so we mentioned object storage devices, OSDs, where the data is actually stored. These can be an entire drive, which that would be ideal to just use one drive for the whole thing. You can also deploy an OSD or use an OSD or use a partition as an OSD. You can also use a folder within a file system as an OSD. The OSDs themselves, they're going to be formatted in a traditional file system, ext4, XFS. You can use Btrfs, but I think at this point it's still kind of experimental for Ceph. In this block diagram, you can kind of see at the bottom you're going to have your drives, your block devices, physical block devices. You can pick your file system, put on top out of your options. And then the object storage device, this becomes your object storage device. So there's going to be on the machine there's going to be an object storage device daemon that's going to monitor the data back and forth. And above that is your data pool or pools. And you can see here that it's actually distributed across OSDs. So in this diagram you don't see like the hosts, you're seeing the OSDs themselves, whether it's a block device, partition, etc. So how is the data organized? Well, the data is partitioned into pools. You can think of pools as just like logical partitions of data. If you want to use some data for some task, you can create a pool for it. And the pools, they contain a number of placement groups. The placement groups are what Ceph objects actually go into. So you don't store objects directly onto OSDs. The objects end up going into a placement group, and then the placement groups get stored onto the OSDs. And you can kind of see here, there's a level of indirection here, so that the client is not accessing the data directly from the devices. Rather, it's kind of getting hashed into these and attached into these. This way, besides the replication being a way to not lose data, it keeps the data from being tied to a single OSD should you want to migrate the data back and forth, or if something goes down, you want to replicate it instead of. At the client levels, when you want to access the data, you can do it a number of different ways. You can access objects directly. You can go into the pool and access them using some of the command line tools. You can access the objects through the Ceph object gateway or the Rados gateway, and this is what gives you that RESTful API that you can use. You can use pools for different managers, for example, CephFS. You can create pools for CephFS, and CephFS will actually require two pools, one for data, one for metadata. So you can see there's a logical partition between two pools there. In a similar manner, the Ceph object gateway does the same thing. You could have like 5 pools, and it will have like buckets and things like that. You can also use pools to create Regal's block devices or Ceph block devices. So I guess technically you could say all of these here are clients. So when I say client here, you're thinking an end user is going to be using these to access the data. But these pieces of software here are actually clients of the pools of data. So it's kind of a different way of thinking of it like that. So this is kind of everything put together. So you can see here we have multiple hosts. Each host can have multiple OSDs if you want. At the pool layer, at the data layer, data layer here, you can see the placement groups they're kind of mapped between different OSDs. There could be on OSDs on the same host, between hosts, etc. The objects are mapped into the placement groups, and then you see how you can access how the clients are going to access the data there. And so you can have multiple pools, as many as you can really fit on the cluster. So replication. So by default, the Ceph pools, they're configured to replicate the data between OSDs. Of course, the idea is fault tolerance. You don't want to lose your data. When you create your cluster, you're going to specify your replication level. By default, it's usually 3. They recommend you have 3 copies of data. Now, of course, this is going to use up a lot of disk space for large objects. You can kind of think of this as like a RAID 1. As many times as you replicate, you're going to have that much division of usable space. So there's actually an alternative to this, and that is erasure coding. The erasure coding is a different way of doing this that's not complete. It's not like a one-to-one replication. It's more like a RAID 5 you can kind of think of, where there's parity information, and that way you don't have to replicate all of the data. Any questions so far? If you want more detail about like the Ceph architecture, there's a lot of information on the Ceph.com website. They go into a lot more details on each point. Any questions before we move on? Okay. So our work with Linaro. So we have a few motivations for this. We mentioned that Ceph is intended to be massively scalable and to be used with commodity hardware. So to use with commodity hardware, that means we should be able to use it on ARMv8 systems. The Ceph clusters would ideally have lots of I/O, storage and network. Ceph itself, when you get to use it, it's a very large system. There's a lot of moving parts, a lot of things that can interact with each other, and it's going to interact with a lot of libraries and the kernel and hardware, etc. And you can see sometimes that if you follow some of the ARMv8 vendors, some of them are targeting these high density, highly scalable storage solution ideas, markets. And the idea is to have like a lot of strong cores with a lot of I/O. So with all those points there, we had some goals. The first goal was really to just bring up a basic Ceph cluster of commodity ARMv8 hardware. So we just wanted to make sure that there aren't any major blockers, there aren't any surprises, just to get it up and running. So we've been able to do that. We've had our cluster up for a while now, probably about a month. It's a pretty basic cluster. There's 3 machines, etc. We'll see about that. The next point was we wanted to look for CPU hotspots when we do our performance testing. So we just wanted to start with some simple workloads. There's some workloads that are built into Ceph that we use, and then we wanted to kind of move on from there. And if we did find any CPU hotspots, the last goal was really to focus on optimizations for AR64. We didn't go into this wanting to optimize the high-level algorithms of Ceph, nor did we want to optimize Ceph for anybody's particular implementation, but rather we wanted to make sure that Ceph runs well on machines in the Linaro Austin colocation lab. We have 4 machines. 3 of them are AMD Opteron A1100 machines, codenamed Sticks. These machines, their cores implement the full ARMv8 ISA, including all the extensions. That includes crypto and CRC. They have 16 gigabytes of RAM. There's 10 gigabit Ethernet available, and we're using these nodes in particular for monitor nodes and OSD nodes. So the data is going to reside on these nodes. We have one other machine, an Applied Micro Exchange Mustang, has 16 gigabytes of RAM, and we're using this as our client/admin node, just to set up the cluster and for us to deploy workloads that affect the rest of the cluster. Each node has one hard drive, 500 gigabytes, 7200 RPM, magnetic drives. They each have one partition that we're using for the OSD. So I mentioned we could use a whole drive or partitions, etc. And each node has one Ethernet connection on a 1 gigabit network. And that's really just a limitation of what's available. There aren't any 10 gigabit Ethernet switches available in the Linaro colocation lab. But this is fine for what we're doing now. So the software we're running, we're using Fedora 21. It has 3.17 kernel. I wrote a ARM64 CRC32 module that's available in 3.19. So that's kind of the hardware accelerated CRC in the kernel. We're using Ceph version 0.91. Now, I built the RPM packages from the Ceph Git repo. Fortunately, the Ceph project, they don't have any ARM64 packages available directly from them. So you have the option with Ceph to either install from your distro or to install from Ceph. And if you use some tools will try to get the latest packages from Ceph directly. In this case, they weren't available. What's available in the distro is version 0.80.7, I think. So we kind of left those and just compiled our own. So we set up a nice little local Yum repo on one of the machines to distribute packages. There's quite a few packages that can be used. There's a tool called Ceph Deploy. If you run through the quick start guide on the Ceph website, they talk about Ceph Deploy. That's kind of the ideal way to deploy a simple cluster. You can use it to actually install packages, to set the keys and config files, etc. So makes things a lot more convenient. But you have to keep in mind also it's going to set up the cluster with some certain defaults. So you can modify those later if you'd like. So our performance testing, collecting data, we went into it looking for kind of the low-hanging fruit. So we started off with some basic performance testing, perf record on the workload. Now on a single node, that's fine, right? You can do perf record on a workload, it's going to collect the perf data. On the cluster, it's a little bit different. So kind of how I do it on the cluster, right? We go to the client node, execute a workload, and depending on the workload, it should be using the cluster. So then for the other machines, you just log into them and you can run a perf top. You can see where everything is, or what's happening. You can see the hotspots bubble up to the top. Now, with the way our configuration is now, we may not get the maximum system load. So if you feel like your performance data is a little bit diluted, you can just kind of zoom in on the process ID. For the OSDs, there's a single OSD process, the OSD daemon that's running on the nodes. So you just monitor that. You can pretty much see all the performance data that's happening at the OSD level that way. So I mentioned earlier, Ceph has some workloads that are built in. One of them is called Rados Bench, and another one is OSD Bench. So Rados Bench, Rados is one of the command line tools that you can use to manually, manage the cluster, etc. It has a command called bench. bench, it acts upon a pool of data. So you see this flag here, -p RBD. That's us specifying a pool of data. So this workload is going to run on the cluster. It's not going to run on a specific node. So the pools of data, this one's called RBD. You can call them kind of whatever you want to call them. You ideally want to call them something descriptive of what they're used for. So for example, RBD could be a Rados block device pool where you put all your block device images. We're going to run for 300 seconds. We're going to do a write. And this will do a write for 300 seconds. So it will return some performance data, how many megabytes per second, etc. If you want to run any read commands after that, you just pass this no cleanup flag. And you can, right after that, you can do some read commands. So these two commands here, sequential and random reads, similar to write, but they're random reads. And the idea is that these commands, they execute on a pool of data which is distributed over the cluster. Another one that's built in or that's available with Ceph is the OST bench. Now this is not a workload that's distributed on the cluster. It's not targeting a pool. It's targeting a specific OST. So if you want to just if you wanted to benchmark, for example, one hard drive on a machine or one OST, however you have that OST configured, you can do that. You can come up with other workloads. So as we just got started, we started with some basic stuff that we did with file system workloads, doing DD, etc. Now, if you're going to use DD, my procedure was pretty simple. I created a Rados block device. So we're using this tool, this command here, RBD create, give it a name and size in megabytes. So you've created a Rados block device. Now the next step is you have this block device. It's a virtual block device, if you can think of it that way. You're going to map it into a pool of data. And as I mentioned earlier, the pools of data, they're just arbitrary names, which you kind of want to pick. You want to logically partition the data so that you want to use them for all the same things. So you might have an RBD, a Rados block device pool of data that you want to put all your block device images in. So you're going to map that into that pool. But then once you do that, now you have a block device, and you can treat it like a block device. So you can make a file system, you can mount the file system, and you can do any operations to that file system. And the work that's done here is going to be distributed across the cluster. So if you do a command here, and you you watch the performance, like perf top on the other nodes, you'll see there's going to be some activity there.
One point there is that doesn't have to be a Ceph file system. It could be any file system.
It could be any file system, right? At this point, it's block device.
Right.
And any file system you want to put on it would make a mess. You can do it. Another thing you can do manually, we mentioned earlier, you can write directly to the pool. It's not necessarily the ideal way of doing things, but you can do that. So you can use the Rados command, you can put an object, give it an object name, and you can tell what file you want to put in that object. And similar to the other commands, you have to specify a pool of data. So you say, I want to put these objects in this pool of data, and you will do that. And this type of command also is distributed across the cluster. Anything you're doing to a pool of data will be distributed. So there are some known optimizations. We're looking for optimization opportunities. There's some low-hanging fruit. The first one was CRC32C. When you do Rados bench, when you do some of the other workloads, you'll see there's a software function with CRC32C that gets called a lot. Fortunately, in ARMv8, there is the CRC32 extension that provides all the instructions for that. So you can accelerate that. So I've already submitted a patch to Ceph to implement that. And along similar lines, there was a patch we submitted to the kernel that's now in 3.19 for the ARM64 CRC module. How does that relate to Ceph? Well, anything that uses that is going to benefit. So Ceph, at the OSD level, the OSDs are using file systems. And if you happen to use ButterFS, you're going to be using a lot of CRC32. I think CephFS also uses CRC32 a lot in the module in the kernel. So that's that. As we optimize the lower levels, we're kind of optimizing the higher levels of the stack. There's other places we could possibly find optimization opportunities. Steve Capper did some work with memcopy. He was using upropt, and he found that, for example, there's a lot of memcopy, but also in particular with Ceph, it seemed like a lot of memcopies were of size 1. And So he was working to see if there's a way to maybe optimize that further, or if that's just a artifact of the way the distributed workload is. So he's working on that. TC malloc, thread, thread coherent malloc, it could be used as a build prerequisite to Ceph. You can build without it, but preferably you'd want it.
That was one of the two changes in the Red Hat and Fedora OSs that you had to disable TC malloc. I think Ubuntu did too.
Oh yeah, okay.
So a whole bunch of people are turning it off and just sort of, oh, it builds fine, and that was something I pointed out in the LAG meeting, that we want to capture the fact that that threaded malloc library is not ported, because I think people just turned it off and forgotten about it. Somebody knows, but
yeah,
not everybody knows.
Right. Yeah, I had some build problems with that where TC malloc's not installed into the room.
Yeah.
So that's we haven't looked into it yet, but it's possible.
Yeah.
The next thing is Boost C++ libraries. Ceph uses those. There's some architecture-specific code in there, so we want to investigate that further. And there's also RocksDB, which is a key store, key value store that could be used with Ceph. That also, I think, uses CRC32 a lot, so that's possible. It's possible we can optimize that further.
Question on your CRC32. So
Sure.
the Ceph element of that, you've requested that to be upstream to Ceph, or are you getting it for free based on the kernel work you do?
No. So yeah. So there's a kernel module that accelerates CRC32. Anybody that uses that will benefit. And some components of Ceph, like CephFS, could use that. And also other components that Ceph is built on top of, like ButterFS, could use that.
Anything in the kernel, any file system.
Anything in the kernel, right. Now, Ceph itself also has its own CRC32 function that they implement in user space. So I wrote a patch for that to implement that, and I've submitted it through the GitHub pull request. So hopefully that will get accepted. It seems like it's passing all the tests and everybody's happy with it, but we just need to get it accepted. Does that answer your question?
Thanks.
And it's not just Ceph, but a lot of different projects, they implement their own CRC functions. I was asked a question actually by a teammate of mine. He was thinking that there was some library that everybody used, which would be nice, but it seems like everybody does their own. So there's a lot of opportunity for CRC. So we had a couple issues when we got started. The first was when we were doing our perf, or recording our perf data, we found that we couldn't decode the Ceph symbols, specifically Ceph binary symbols. Everything else was being decoded, just not Ceph. And it wasn't a particular binary either. It was kind of a number of different libraries, etc. So if we couldn't decode that, we don't know where the hotspots are. It was kind of difficult to kind of figure that out. Steve Capper actually wrote a patch against perf that kind of worked around the issue. And but the behavior is still kind of weird in that sometimes the workaround works. I've had cases where it works and other times it doesn't. And then passing different flags works, etc. So that's something we want to look into more. There's a pretty common bug with Python 2.7. If you use Ceph, you might notice on some distros that you will try to run a Ceph command and it will hang. It'll never complete. So that's a bug in Python 2.7. It's been fixed in Python 2.8. And also Ceph upstream, they worked around that issue. So if you're stuck at that kind of thing where you see things not completing, either get a later version of Ceph or Python. Now there's some limitations with what we have right now. The most obvious to us is we're I/O bound. We have a single OSD on a single partition on a single hard drive, a magnetic hard drive, and we're running all this on a 1 gigabit network. So for our basic testing, this is sufficient because we're looking for the low-hanging fruit. But as we want to find corner cases and more, advanced optimizations, we may want to, expand our hardware. A lot of machines now can put 8 hard drives or more on a node. So having 8 or more SSDs, with each SSD acting as an individual OSD rather furthermore, enabling or using a 10 gigabit network to support the nodes. Just to do these together so that neither of them is pounding the other. Another point is having more nodes. Right now we have the 3 AMD Seattle nodes and 3 AMD Seattle nodes and 1 APM node. But the more nodes, the better. The more advanced things you could do, and the more you approach kind of a representation of what a data center would do. So the more we have, maybe the better we can profile.
And I mean also the more different implementations.
And the more implementations, the better. Yeah. Then we can, the idea there, so we don't want to optimize for a specific implementation, but if we see something benefiting everybody, then we want to go for that.
You know, fun thing was the high keyboard has CRC
That's good.
extension, so we could build a little tiny, just for fun, right? That's kind of
USB Ethernet.
Yeah, USBs.
CRC is used in surprisingly a lot of places, so it's good.
Just a quick question on the Python issue. Is that an issue in core Python or the way Ceph was using Python?
I think both. So I think the way it worked was, the issue was some Ceph processes, when they exit, they would spawn a thread. And there was an issue with Python where that broke. There was some patch that was submitted to Python that broke that. And you can either back out that patch and rebuild Python and it will work, or you can use a later version of Ceph where they worked around it and they don't do that anymore. So it's kind of a two-way thing, or either or.
Because I see something similar where it's running in Tempest. It's not all the time.
So it could be, yeah. I can get with you. It can get you. Well, I think in 2.8 they fixed it, or I can get you the backout patch to kind of fix that. So some future work we're scoping out. The first thing is Toothology. Now, Toothology is kind of the Ceph test suite tool. The idea there is we want to bring it up on ARM-V hardware, just like we brought the Ceph cluster, make sure there aren't any blockers, they're obvious. And then run through the suite of tests, make sure all the tests work. And possibly, implement any AR64 specific tests, if there are any that we can do. So that's one of the next things on our roadmap. So we also have further workload profiling. So I haven't really touched Cephfs, but that's definitely an area we can look into. There's the Ceph Object Gateway, Rados Gateway. I actually have this enabled on our cluster now, but it is not actually talking to anybody else, but I can use it directly. So, like for example, Object Gateway, hooking that into OpenStack, then we can deploy some OpenStack workloads and using Ceph as a backend. So there's some interesting, workloads we can run there and maybe see some, different behavior. There's the Ceph prerequisite, so we can see on AR64. The most obvious is the Boost C++ libraries. Now, that won't just benefit Ceph. Of course, that'll benefit anybody who's using that. So this might be an opportunity for us to dig into that further. And then there's TC-malloc. We'll look into that further also.
Is the boosting or TC-malloc on anybody's radar? It's not yet, right? The AIG?
I don't know if it's official, but it's kind of, one way to think of it is when we find an area that might be interesting, we'll open a card and we'll investigate it further. So there's kind of like there's this kind of monolithic card that's kind of overall exploration and benchmarking, and then from that spawns multiple cards and things. So if we find anything interesting, definitely it'll get on people's radar. And that's all I have right now. And any questions?
I've got a couple of. Anyone else go first?
Yes.
Surely the boost thing, it should be on the toolchain guys radar, right?
I'm sorry?
The boost library thing, that's typically something that the toolchain guys should be aware of.
The toolchain guys?
Yeah.
Yeah, I wouldn't be aware of that. I can look into it. But that seems like, something to look into. Any other questions, comments?
Do you have any, just in the infrastructure you're running in right now, do do we have the right time servers set up for keeping the nodes in sync? Is the network infrastructure good enough for what you need?
I mean, it's a pretty small cluster, and I haven't seen any issues. Like the health of the cluster comes back as healthy.
Okay.
It's okay. There hasn't been any weird fallout or dropout nodes or desyncing or anything like that. So it seems okay for what we have right now.
We have NTP servers inside Linaro.
No, I mean I haven't hooked into any local NTP servers, so I'm not sure.
We'll probably want to set something up because some of the hardware coming in doesn't. The early versions of hardware often don't have RTCs wired up or working, so
Okay.
you boot them and then it thinks it's 1969, right? And then they drop out of the cluster.
Right.
This I have seen.
Yeah.
So,
Yeah, I haven't had much problem with that, or I haven't had any problem with that. Once it seems pretty stable. Our infrastructure guys, they do a good job about provisioning the machines and
yeah.
getting them to be. They're pretty stable. I mean,
So they hand them off to you. So they do an install and say, here's a sort of installed OS. That's
Right. Yeah. So I
okay.
think the mandate for the Linaro Colo lab is that they're catering to ISVs.
Right.
So they're handling all the hardware. They just do a fresh install of whatever OS you want that they have available, and then they give you full control over it. And I think they're going to go public with that soon, or they're going to push it even further as soon as it's already public.
Right.
Yeah, I haven't had a problem with their infrastructure so far. It's been really stable. Anything else? All right. Well, thank you very much.